we talked about diagonals, and if you remember, a diagonal, in the sense of how we're going to use it, and I guess regardless of how you use it, but we're only going to use it from one vertex. Okay, so if I look at the quadrilateral, okay, the orange figure up there, 4 sides, there are 2 diagonals that we could draw. I only want to draw one of them. Okay, if I look at the pentagon, there's 1, 2, 3, I think 4, maybe 5 diagonals that we draw there. But I only want to draw a small amount of them.
Just trying to learn.
Oh, okay.
No, trying to see you for a second. Can I see you?
Yeah. So we're going to start at one vertex and draw all the possible diagonals from that one vertex. Okay. I don't want you to go and draw all the diagonals from one vertex, and then go to another vertex and draw all the accompanying diagonals that can be drawn there, and then go to the next vertex and draw all the accompanying diagonals and go from there, because that's going to create a cluttered mess for you. Okay. And it's not going to lead us to anything useful. Okay. So what I'm trying to say, just give you a visual here. If I'm going to work in this figure over here, I'm going to start at Z, and I'm going to draw all the diagonals that can go from Z, okay? Does that make sense? What I don't want you to do is then go to W and draw all the diagonals that exist from W, okay? Because you start to see that it's getting very, very messy, right? And I don't want you to go to V and then draw all the ones that go from V. That's really a pain in the butt. All right. So we start at one vertex, and it doesn't matter which one, and then we go to the non-consecutive vertices. Okay. So if I start with the triangle one, a triangle has no diagonals. Okay. You cannot start here and go to a non-consecutive vertex because C and A are the only 2 options, and they are both consecutive. Does that make sense? So no diagonals there. If I start, maybe I start over here, F, what vertex do I have to go to get the diagonal? D. Okay. What if I start at J over here? Where could I go? H or L. Okay, those are my 2 options. And then, I think you guys are getting the hang of it. So I'll just quickly do that. Is that doable? Okay. Now what we're interested in, the reason I'm showing this is because I'm interested in how many sides we have in each one of these figures. So, and I'm going to call that N. So the number of sides in the first one is 3, right? How many triangles does that provide you with? 1 triangle. And how many degrees are in that 1 triangle? 180. Okay. Over here, in the quadrilateral, how many sides do you have? 4. How many? When I draw the diagonals, how many triangles does that give you? 2. So there's 180 degrees in that triangle and 180 degrees in that triangle, right? So how many degrees are there in the quadrilateral total? 360. Okay. Come over here. We've got, let me slide this thing up a little bit. We've got N to be 5 sides, right? So it's a pentagon. How many triangles does that give you? 3 triangles. How many degrees would that be then if each one of those is 180 degrees? 540. Okay. Come over here. N is 6. How many triangles do you get? Be 4 triangles, right? Okay. Each one of them being 180 degrees. Would you guys agree that that then gives you 720? And then over here, we go N is equal to 7. Gives us how many triangles? 5 triangles, right? And then if you take 180 plus 180 plus 180 5 times, you would get 900 degrees. Okay? Now, what I want you guys to realize is that when I tell you that you have a heptagon, a 7-sided figure, you automatically should know that that's 900 degrees. Okay? I don't want you to have to memorize that, though. Because if you start thinking about, it's common knowledge that a triangle has 180, right? Okay. Maybe it's common knowledge a quadrilateral has 360. Okay. But at some point, it's going to stop being common knowledge to know that maybe a dodecagon has 1,800. Okay. Maybe you don't know that. Okay. So I don't want you to memorize these because where do we stop? Okay. Do I stop at 12 sides? Do I stop at 30 sides? Do I stop at 3,000 sides? In regards to memorizing how many total degrees are in the figure. Okay. So what we do is we use the pattern that we just set up. It's called induction. Okay. We see that there's a consistent pattern going on here, right? Okay. If I have n to be 3 in that first triangle, okay, or first polygon, if n is 3, you get 1 triangle, right? Go to the next one. If n is 4, you get 2 triangles. Go to the next one. N is 5, you get 3 triangles. Go to the next one. N is 6, you get 4 triangles. What's the pattern for determining the number of triangles you get based off the number of sides that you start with? What do I need to subtract from 3 to get 1? 3 minus 2, right? What do I need to subtract from 4 to get 2? 4 minus 2, right? What do I need to subtract from 5 to get 3? 2, right? 6 to get 4, subtract 2. 7 to get 5, you subtract 2, right? Well, that 3, the 4, the 5, the 6, and the 7, those are simply my n values, aren't they? So my number of triangles, okay, this portion here is found by simply the expression n minus 2. Okay, and really that's developed because in my polygon, if I have n vertices, there are 2 vertices that you cannot draw diagonal to, right? Okay, so that eliminates the possibility of having n triangles. We now only have n minus 2 triangles possible. And then to figure out these degrees, okay, well, the n minus 2 creates a number of triangles. Each triangle itself is 180 degrees, so didn't this 180 get created by taking n minus 2 times 180? Didn't this get created by taking n minus 2, which would in this case been 2, and multiplied that by 180? This one here is my n minus 2. Okay, now it would have been 3 times 180. Okay, so that gives me 540. So in each one of these, we see that the formula is consistent. Does that make sense to everybody? So if I want to find the total number of degrees in, let's say, a 30-sided figure, you don't want to have to draw out 30 sides, do you? Okay. You now have a formula that allows you to do it. If I have a 30-sided figure, I want to know how many total degrees there are in there. Okay. That's going to give me n minus 2 triangles, so it's going to be 28 triangles. And I take those 28 triangles and multiply by 180, and it tells me how many degrees then are in that 30-sided figure. Does that make sense? Okay. Some of you might say, well, 30 sides isn't bad. I can do 30 sides. I can draw that. Well, then I'm going to say, okay, let's draw a figure that has 30,000 sides. You want to draw that? Probably not, right? But this formula allows us to investigate and deal with that figure that is beyond the size of anything that we want to deal with, okay? Graphically, okay? But we can still use the formula to know how many degrees are in that figure. Is that all right with everybody? Okay. So n minus 2 times 180 degrees is the total, you might want to write this down, this is the total number of degrees in a convex polygon. And maybe you even want to make note that we're talking interior degrees. Degrees on the inside of the figure. N minus 2 times 180. Becomes a very useful formula for some of the problems that we do. But what is happening now, if you remember back to what we dealt with in regards to triangles, the style of problems we solve with triangles, if we know that 3 angles of a triangle add up to 180 degrees, and I give you 2 of them, can you automatically find the third one? By subtracting the 2 that you know from the total, right? Well, now if I give you a quadrilateral, and I give you 3 angles of the quadrilateral, can you find automatically the fourth one? By subtracting the sum of the first 3 from 360 now? And you can do that with any polygon as long as you know the total. So to know the total, you have to use the n minus 2 times 180 first, get your total, and then subtract the known values that they provide you, and that should give you the remaining angle. Okay? We'll see a couple examples of that here in a little bit. What I want you guys to understand, though, let me clean some stuff up here and deal with just one of these figures. When we're trying to find the total number of angle measurements, we are looking at those angles. Okay, those green angles are what we're looking for. And regardless of how the figure is set up, I'm going to try to keep it convex. Okay. You see that this 128.57 degrees. Okay. When we use the n minus 2 times 180 formula, that 128.57 degrees is broken up and is part of 1, 2, 3, 4, 5 different triangles. But when I put those 5 triangles back together and they all meet here at this vertex, that sum of that angle for the polygon is 128.57. Does that make sense? For instance, this angle up here, this 125, it's part of 2 triangles. So it was part of the 125 is in this 180 degrees, and the other part of the 125 is this 180 degrees. But back together, when I get rid of essentially the diagonals, you see it, those totals still remain, right? Is that okay with everybody? And I want to show you just algebraic. It's going to be kind of a pain in the butt. So just give me a minute here. Alpha, beta. All right, just trying to recall all of these angle measurements. Okay, so all I did is I asked GeoGebra basically to take all these numbers over here in this column and add them together, and in this case you get 900. Well, if I take n minus 2 times 180 in this particular picture, n being 7, I get 5 times 180. Well, 5 times 180 is 900. Does that make sense to everybody? Okay. Now, as you see, when I start moving things around, does that 100, as long as I keep this convex, and even if I make it concave, we still get the same relationship. But do we see that 900 ever changing from 900? No, it's always going to be 900 because it's always a heptagon, right? Or septagon, whatever you want to call it. 7-sided figure. Okay. The reason I want to talk about it and maintain it as convex is because when we do this, okay, we still get 900 degrees here, right? Okay. But we look at this angle here of 232.63 is bigger than the 180 degrees that we've been talking about. Okay, so I want to deal with, right now, just convex polygons. Is that all right with everybody? Okay. Now, what we like to do, we can deal with convex polygons, and the idea is what I said earlier. Let's say that I hide that angle right there. I don't tell you that one, but you know the other 6. Can you add those other 6 together and then subtract that quantity from 900 to give you angle A? Okay, so regardless if they start with a 5-sided, 6-sided, 7-sided, 3-sided, whatever, if you know the total number of angles and they give you all but one angle of the figure, you should be able to come up with the missing one. Okay, so that's important. The next thing I want to talk about is the situation when that figure is regular. Remember what regular meant was that every single angle and every single segment were the same measurement. Okay? So now when I look at that heptagon, still 7 sides, what should all 7 angles add up to again? Should still up to 900, right? Okay, so if I add 128.57 plus 128.57, I do that 7 times, I get 900. Okay? But what is when it's regular, you see that they're all the same, right? That's what we talked about. Regular means they're equal angular. Okay? How can I find, let's say I didn't know those. Let's say I didn't know those angles, but I did know it was regular. How could I find one of those angle measurements? Okay. We have a formula that says n minus 2 times 180. That will give me the 900, right? That will give me the total for all 7 angles. Okay? But I only want to find one. But all 7 of them are the same. So what do I need to do with that n minus 2 times 180 to find just one of the 7 angles? I want to divide by n. Won't that give me the average? Okay. If they're all the same, and I know what they all add up to, but I only want one of them, I'm taking an average. Okay. So n minus 2 times 180 tells me the total, 900. Okay. Those 7 angles are all the same, so I take the 900 divided by 7, and I get my, in that case, 128.57. Okay. It's the same idea, the same thing we did with equal angular triangles. With an equal angular triangle, you take 180 and you divide it by 3, right? Okay, because all 3 angles should be the same, so 180 divided by 3 gives me 60. That's just now with the heptagon, every angle is 128.57, if it's regular. Okay, is that doable? So in your PowerPoint, you see those 2 formulas. The key thing is that we're, in the first one, the n minus 2 times 180, we're talking about convex polygons, okay? I don't think any of your problems in your homework give you concave polygons to work with that formula, okay? In the bottom one, it has to be a regular polygon, okay? Regular means it's convex, doesn't it? Okay? Every regular polygon is convex. You might want to write this down. Every regular polygon is convex. Okay. However, is every convex polygon regular?
No.
No. Okay. And that's important. That's what I said yesterday. That in this chapter, what gets people kind of tripped up and that they have issues with is all the different kind of perspectives that we take and look at these statements. Okay. Every convex polygon, when I start with a convex polygon, it does not mean that it's regular, okay? But if I have a regular polygon, it meets the requirements of being convex. Therefore, every regular polygon implies that it's a convex polygon. Is that okay with everyone? So those are some things I'm going to ask you to understand and to be able to deal with in regards to maybe the way I present a question. In the vocabulary that I use, and it tells you maybe the route and the formulas that you might be able to use to analyze the question. So here's just an example. This is, I think, probably some of the easier questions maybe you saw from last night if you started that assignment. But here we've got a pentagon, right? We got five angles, 5 sides. How many degrees should there be in a pentagon?
540.
540. Okay. You have 4 of those angles up there, right? Can I take 540 minus 110, minus 90, minus 120, minus 150 to get angle Y?
Yes.
And I think in that case, if you do that, angle Y ends up being 70 degrees. You just subtract. You missed the 110. So it is 70. Okay. Same thing on this example. Now it's a quadrilateral. So now the total changes, right? That's what you need to make sure you pay attention to as you do these problems in the past. Somebody would do like question 4 might say it's a quadrilateral and they get 360 stuck in their mind and then they use 360 for every problem after that. Okay? You need to understand that as the shape changes, your total changes. The n minus 2 times 180 is going to change from shape to shape. So you need to keep that in mind as you do your homework. This theorem, we're almost done here. But this theorem says the sum of the measures of the exterior angles of any convex polygon, one angle at each vertex is 360 degrees. What that's saying, and we've done this before, if you guys remember back to, actually we'll do this, it's easier if I go to this. The www. All right, so I've got those exterior angles. Okay, I got a triangle, right? Those exterior angles, they're all different. But if I take those exterior angles, and you can take your calculator, you can verify this, but 141 plus 140 plus 79, it's going to give you 360 degrees. Okay? As I change the triangle, okay, it changed the individual angle measurements, right? The exterior angles, but what do they still add up to? 360. Okay? And we talked about that earlier when we talked about remote interior angles for triangles. We actually talked about this briefly. But no matter how you change these, you get 360 degrees. The idea is, though, that we want to make sure that we're only talking about one angle at each vertex. Okay? I don't want this. Does that make sense? Because what's that all going to add up to? If I look at all those. 720. It's double everything, right? Okay? So I either go, here it's showing you going counterclockwise and getting those exterior angles. Here it's showing you going clockwise and getting those exterior angles. Okay? Regardless of the ones I use, you still see they're using the same exact values, right? Okay? We just don't want to use both and double them up because, look, they're vertical, aren't they? So they should be the same. Okay? So in a triangle, they add up to 360. Cameron?
So the angles on the inside, they would add up to 180, right?
Yes, the angles on the inside are going to add up to 180. Okay, for a triangle. Now if I add sides, okay, now all those angles are different, right? All those exterior angles are different. What do they all add up to?
360.
360. What are the angles on the inside going to add up to?
360.
360, because it's quadrilateral, right? Okay. Now as you move these around, you can change them. Okay, still get 360 as a total, right? The only thing you need to be cautious with here is that we can deal with this in regards to concave, but then you see in the formula that when it's a concave angle, we still extend a side, but it's not necessarily maybe on the outside anymore. I don't know what you would call that. Okay, but you see in the formula how that 32 is now getting removed, right? It's a negative 32 degrees. So we're not going to deal with that. Okay, we're going to deal with just convex polygons. Okay, so 360 degrees. Add sides. Does that total change? Nope. Add sides. The total change? Nope. So regardless of the number of sides you have, you're going to have a total of exterior angles after 360.
Wait, so the inside's still like smaller though, right?
Well, yeah, the inside. Okay, so right now we've got 7 sides, right? So the 7 angles on the inside are still going to add up to 900 degrees. Still going to be the n minus 2 times 180. I can make this regular. Okay? If I make it regular, I'm taking 360 and dividing it by what to get that 51? If it's regular, the inside angles are all the same, right? So isn't every interior angle a supplement to an exterior angle?
Yeah.
So if that angle right there, let's do,
It would be
I think we found it was like 128.57 or something like that. Okay? If that's let's just say 129. If that's 129, that's got to be 51, right? If that's 129, that's got to be 51. If that's 129, that's going to be 51, right? So in a regular polygon, the exterior angles are all the same as well. Okay? You take 360 divided by however many exterior angles you have, and that gives you one exterior angle measurement.
Did you just come up with that number, Justin? Yes, sir.
Hmm?
Did you just come up with that number, 129? That's what it
No,
is.
we did it earlier.
Oh,
The more and more sides that you add, what is happening to the exterior angle measurement?
it's smaller.
Smaller and smaller. And I'm going to ask you that question on a test or quiz, okay? When you're dealing with a regular polygon and you start to increase the number of sides, okay, what happens to each individual exterior angle? And it decreases, okay? That's a relationship of variation that's important. What is, now I'm going to say that I'm going to restrict the size of a diagonal. Say, like right now, a diagonal, maybe the largest diagonal would be that distance right there. Would you agree with that?
Yeah.
Okay. Let's say I'm going to force that distance to be maintained. I'm just going to try to keep it that in the ballpark of that, whatever that length is right now, so that this shape doesn't grow outside the screen. The more and more sides that I add, what does the polygon start to look like? The more and more sides, it becomes a, well, the sides become these angles, but the shape is evolving into a circle, right?
Yeah.
Okay. Those of you that like watch, watch animation like Pixar and stuff like that, movies. Okay. They do a lot of this type of stuff where they start with a very rough polygon-shaped figure, and they start taking midpoints and quarter points and averages, and they start to round off those shapes so they look lifelike and not polygonal. Does that make sense? So there's a lot of geometry and mathematics in the development of those characters that you see in those movies. Now, kind of a calculus concept, I could put 1,000 sides in there, and it's still a polygon, okay? And if I put 1,000 sides in there and I make it the size of Allen County, it's going to look like a polygon, okay? But if I put 1,000 sides on that and I make it the size of Allen County, but I'm looking at it from an airplane, okay, that's 2 miles in the air, it's probably going to look like a circle, right? Because the distance between me and that shape now is increased, and the individual segments, the 1,000 segments that make up that polygon, are very, very small now, and it's going to look circular. That concept, that understanding of those size differentials and how the shape can change from a polygon to maybe visually a circle, depending on how I look at it, is calculus. Okay, kind of give you an idea of this. We have, this is the concept. That's a circle, right? Okay, and if I look at it from afar, it looks like a circle, right? If I zoom in on it, what's that portion of the circle look like now? Does that look like a segment? Straight line? Okay. But the further you are away from it, you start to see the curvature. The closer you are, you don't see the curvature. Okay. And that's the kind of the concept of, or one of the many concepts that you talk about in a calculus course. One last kind of example here. We'll do this two different ways. You'll see some of these in your homework. It says, if you have a polygon with one interior angle equal to 150, name the polygon. When you name polygons, and you're going to see a lot of different questions that ask you to do this, you first have to know the number of sides, right? That's how we dictate a polygon. So we're looking for n. Well, we have some formulas that deal with n. We specifically have a formula that says n minus 2 times 180 over n is equal to an interior angle. Okay, I should say here that this polygon is regular. Okay, if I said it was irregular or I don't know whether it's regular, I tell you one angle is 150. you have absolutely no way of knowing what the other angles are. So you couldn't do this problem. You have to know it's regular. So all angles inside this polygon are all 150 degrees. We just need to figure out how many of them there are. Okay? So using this formula, there's two approaches. This is the longer approach, but I want you to see this because you need to be able to do this algebra, not just for this class, but other courses. N is a variable, and interior angle is also a variable, right? We're looking for n. So that's going to maintain, this n is going to stay as n throughout our work. So that means I must have a way of changing this variable, the interior angle, to a number. What is that number? It's 150, right? Okay. So we get this equation. And the reason I show this is because this is a rational equation. It has ratios and fractions in it. When you have ratios in your equation, what you want to do is get rid of those fractions as fast as possible, right? What would I need to multiply everything by, or both sides by, so I can get rid of that denominator? N, okay? Multiply, n is representing a number, right? So we treat it like a number. If it was 2, we'd multiply both sides by 2. If it was 3, we'd multiply both sides by 3, right? Okay? We would triple it, or quadruple it, or double it, or whatever, in order to get rid of that denominator. Well, now we're just going to n whatever that side. So multiply that side, the left-hand side, by n times, and then do the same thing to the right-hand side, and that should do that task of doubling or quadrupling or tripling or whatever both sides, and it gets rid of those n's. Does that make sense? So now you're left with n minus 2 times 180 is equal to 150n. So now you have a linear equation, multi-step equation, very easy to solve. What can I do with this 180?
Distribute it.
Yep, I'm going to distribute. So 180n minus 360 is equal to 150n. And I think at this point, most of us are probably comfortable with moving the 180n to the other side. Now they're both negatives, right? So essentially they're both positives. And then when I divide both sides by 30, I get n to be what? 12. So n is 12. So what's a 12-sided figure called?
Dodecagon.
Good. Dodecagon. Okay. As you're doing these problems, if you get anything beyond 12, if you get 13, call it a 13gon. If you get 14, call it a 14gon. They're not going to ask you. They might ask you to type in dodecagon or choose it from a drop-down window or something like that. But beyond that, it'll be 14gon, 15gon, that kind of thing. All right, there's an easier way. There's an easier way. Okay? And I don't care which approach you guys use, but if I have a regular polygon and I know one interior angle is 150 degrees, do you know what the exterior angle is?
Yes.
What?
40.
Okay.
Right, 30.
30, okay? You know an interior angle and exterior angle are supplementary, right?
Yep.
So you know the exterior angle of this regular polygon is 30. One of the exterior angles is 30. What are all the exterior angles? No matter how many you have, what are they all supposed to add up to? 360, right? If all of them add up to 360, and you've got one of them that is 30, and you know all the other ones need to be 30 as well, what can I do with that 360 and that 30?
Add up till we said 48 equal 360.
If I divide them, don't I? 360, that's my total. Divide it by one of the objects. And if all the objects are the same, I should get a result back that tells me how many objects I had. So 360 divided by 30,
12.
oh, gives me 12, right? And that 360 divided by 30 is the exact same 360 divided by 30 that we got down there. But we got to that point maybe using a different route. Does that make sense, everyone? Okay. I don't care which route you use. I'm thinking that most of us algebraically would probably prefer the one on the right, correct? A little bit quicker, a little bit easier. But show that algebra on the left because that is important for us to be able to manipulate equations like that later on in this course and in other courses. Okay? You should be able to finish up that assignment from last night. We're going to move on to 6.2 tomorrow. Hopefully you know your vocabulary from section 6.1 tomorrow.